This paper, titled Introduction to the Auxiliary Modulation Coordinate, a Reduction to Quantum Mechanics, authored by Christopher Young, proposes an extension of quantum field theory by introducing an additional dynamic dimension called the modulation coordinate. The purpose of the paper is to develop a comprehensive theoretical framework that elevates modulation from a mere parameter to a full dynamical field coordinate, thereby providing a deterministic underpinning to quantum phenomena and potentially resolving foundational issues in quantum mechanics. The work builds on established quantum field theory principles, particularly those developed by Weinberg and Peskin and Schroeder, who laid the mathematical foundations for field propagation and oscillator treatments in spacetime. Young's approach introduces a third dynamic axis, modulation, while preserving similar differential equation structures. This auxiliary modulation coordinate framework shares conceptual goals with deterministic interpretations of quantum mechanics, such as Bohm's hidden variables and 't Hooft's cellular automaton, but differs fundamentally by treating modulation itself as the guiding principle without requiring separate hidden variables or discrete computational models. Additionally, Carroll's recent work on the emergence of classical reality from quantum fields, which emphasizes decoherence, contrasts with Young's theory, which posits modulation coherence as the fundamental organizing principle. The introduction highlights a key departure from conventional quantum field theory as presented by Griffiths. Traditionally, fields propagate in spacetime with fixed parameters, but Young argues that modulation depth, a parameter controlling envelope structure and coherence bandwidth, must be elevated to a physical dimension to fully explain quantum phenomena. This move aligns conceptually with efforts to restore determinism to quantum mechanics, but differs in positing continuous modulation fields as the substructure rather than discrete computational entities. Comparisons are also drawn with Zurek's decoherence framework, which treats classicality as arising from environmental entanglement. Young's theory inverts this causality by suggesting that coherence maintained by modulation dynamics is fundamental, and decoherence arises when these dynamics fail. Mathematically, the auxiliary modulation coordinate field equation resembles soliton equations studied by Rajaraman and Yang, known for stable, localized solutions. However, while soliton theory focuses on nonlinear effects within standard spacetime dimensions, Young derives similar structures through interactions between spacetime and modulation dimensions, implying that soliton analysis tools might be adapted to this new framework. The foundation of the theory starts with a generalized modulation-based field defined as a field potential dependent on space and time, modulated by amplitude and scale parameters that initially act as modifiers rather than physical dimensions. This resembles quantum optical systems studied by Longhi, where physical modulation simulates quantum effects. Young's approach reverses this relationship, proposing that quantum effects arise from fundamental modulation structures, suggesting experimental possibilities via optical analogs. However, this initial formulation cannot fully model phenomena such as wave function collapse, information propagation, coherence decay, and rotational dynamics. To address these, modulation must be treated as a full coordinate. This promotion from parameter to dynamic field coordinate has precedence in theoretical physics, such as scalar tensor gravity theories and effective field theories, where coupling constants become dynamical fields. Young applies this methodology in a novel context focused on quantum modulation. The field is thus redefined to depend on space, time, and modulation, transforming modulation from a passive parameter into an active axis of field evolution. Analogous to spatial and temporal derivatives governing variations in space and time, the modulation field obeys a second-order differential equation incorporating a modulation length scale and a stabilization term. This stabilization term prevents uncontrolled divergence in modulation space, bearing conceptual similarity to renormalization techniques in quantum field theory, but representing a physical constraint on modulation propagation rather than a mathematical fix. From these considerations, Young derives the auxiliary modulation coordinate field equation, a second-order wave equation involving spatial variation, modulation curvature, a stabilizing potential, and source terms comprising a modulation-dependent current and harmonic driving functions. This equation governs the evolution of the field potential simultaneously across space, time, and modulation depth, forming a three-axis resonant structure. The paper then demonstrates how quantum mechanical behavior emerges as a limiting case of this more fundamental theory. By treating modulation as the full quantum wave function and assuming low-energy, slowly varying modulations, the auxiliary modulation coordinate equation reduces to the Schrödinger equation. This aligns with Adler's view of quantum theory as an emergent phenomenon from deeper deterministic dynamics, though Adler's approach involves non-commuting matrix variables, whereas Young's focuses on modulation fields. The two approaches may offer complementary insights. Young's theory addresses the measurement problem by proposing that wave function collapse results from failure of modulation resonance triggered by interactions with measurement apparatus. This offers a specific physical mechanism absent in many mainstream interpretations, which typically rely on decoherence alone. The deterministic modulation dynamics provide a substructure from which apparent quantum randomness emerges, resonating with Palmer's ideas linking determinism, chaos, and quantum mechanics. The auxiliary modulation coordinate framework gives rise to four primary dynamic processes, each corresponding to specific field behaviors. First, information flow and coherent stabilization governs the organized propagation of quantum information across modulation and time. It maintains phase locking of energy packets, preventing decoherence. This process is derived from the source current and modulation function, ensuring conservation of structured informational states. The theory connects with quantum coherence as a resource in quantum information theory, suggesting that experimental quantum error correction techniques effectively reinforce modulation coherence. Empirical work by Kelly and colleagues on superconducting circuits demonstrates functional parallels with this dynamic process, indicating that current quantum technologies may implicitly exploit modulation dynamics. Second, baseline resonance stabilization functions as the carrier frequency or ground state oscillation of the modulation field. Unlike the static vacuum in conventional quantum field theory, this baseline resonance is inherently dynamic and essential for maintaining coherence. It emerges from sinusoidal components and phase-anchored standing wave solutions of the homogeneous auxiliary modulation coordinate equation. Weinberg's studies on vacuum stability relate conceptually, though Young emphasizes resonant synchronization over energy minimization. Experimental observations by Martinez et al. On decoherence in Josephson qubits, attributed to material imperfections disrupting coherence, can be interpreted as disturbances to this baseline resonance, suggesting experimental avenues to test the theory. Third, rotational modulation derives quantum spin and related phenomena from rotational phase coherence within the modulation field, providing a physical mechanism rather than treating spin as an intrinsic, axiomatic property. This process arises from the curl of the time derivative of the field and sinusoidal driving terms, involving cross terms between space and modulation in rotating solutions. The framework aligns with Rovelli's relational quantum mechanics in emphasizing contextuality, where quantum state's meaning depends on reference frames and relative phases. Berry's geometric phases, which emerge from cyclic adiabatic evolution in parameter space, find a parallel here as manifestations of fundamental modulation geometry, suggesting that rotational modulation offers a deeper explanation for these quantum phases. Fourth, structured localization describes stable, localized regions of energy and structure in the modulation field, analogous to but physically distinct from topological solitons. These localized structures emerge as solutions to the auxiliary modulation coordinate wave equation under radial symmetry, exhibiting exponential decay envelopes. They form the basis for persistent quantum particles, memory registers in modulated artificial intelligence systems, and biological quantum information centers, such as neural coherence. Experimental research on optical quantum memory systems by Lvovsky, Sanders, and Tittle supports the existence of such localized quantum information structures, implying that different physical implementations share the common principle of stable modulation structures. A summary table in the paper encapsulates these four dynamic processes: information flow and coherent stabilization, baseline resonance, rotational modulation, and structured localization, each originating from distinct physical and mathematical features of the Auxiliary Modulation Coordinate framework. In conclusion, Young emphasizes that the Auxiliary Modulation Coordinate field equation is not an independent theory but a natural expansion of the generalized modulation-based field equation once modulation is treated as a full dynamical coordinate. This elevation transforms amplitude and frequency envelopes into a differential geometry of coherence, energy localization, and quantum structure. The resulting second-order wave equation couples space, time, and modulation depth, offering a comprehensive physical interpretation that addresses foundational quantum questions, including measurement and determinism. The theory shares conceptual goals with the amplituhedron program of Arcani, Hamed, and Trinka, which reformulates quantum field theory through geometric objects to simplify amplitude calculations. While the amplituhedron focuses on computational advantages, the auxiliary modulation coordinate theory provides a physical interpretation that seeks to explain quantum measurement and determinism. This suggests potential cross-fertilization, where geometric insights from the amplituhedron might inform modulation dynamics analysis. Furthermore, the paper connects to quantum simulation research, highlighting that engineered quantum systems with fine control over coherence and decoherence could serve as experimental platforms to test predictions unique to the auxiliary modulation coordinate theory. Though conventional quantum mechanics and this new framework often align in simple systems, carefully designed quantum simulations might reveal divergences, offering crucial empirical tests. Overall, this work proposes a mathematically rigorous and physically grounded extension of quantum field theory that elevates modulation to a dynamical coordinate, yielding a deterministic substructure from which quantum mechanics emerges. It provides explicit mechanisms for coherence, measurement, spin, and localization phenomena, and suggests experimental pathways for validation, potentially advancing foundational understanding in quantum physics.